Welcome to Seattle Atheist Church. Atheist, agnostic, skeptic, whatever you like to call yourself, you are welcome here. At Seattle Atheist Church, we call ourselves an atheist church because you will never hear anything supernatural promoted from the podium. Our church was founded on the principles of scientific naturalism and secular ethics. Truth claims are attempted here, and we stand ready to revise our thinking in light of new information. We attempt to be excellent to all conscious beings, and we believe in good, because good works in non-mysterious ways. If that sounds good to you, then you are probably in the right place. So in terms of some upcoming events, next Friday we are going to be having a movie night. The movie is about the investigative team that broke the story about some of the abuses that were happening in the Catholic Church. If you're interested, please go to the website and sign up for that, and then information will be sent to you. Okay. The third Saturday of every month, we have a secular social at Browers at 3 p.m. It's 21 and older. And also next week, we're going to have a talk called Emotional Intelligence 101. The following week, we will have our planning meeting, and everyone is invited to come to the planning meeting. So the way we do it here is the members ourselves give the talks, so there'll be different talks every week, and then afterwards we'll get into a circle and we'll have some discussion time. Without further ado, Bradley, Extra Solar Planet System.
Hello. Okay. Yeah. Over the last 20 years, there has been a lot of popular interest in discoveries of planets orbiting stars other than our own sun. We are interested in knowing what is up there or out there, especially if it might be alive. Planets are interesting, but ones that might harbor life more so. I will start with a brief account of the theories that scientists use to explain the existence of planets. Most scientists believe that planets formed out of the same clouds of gas and dust which gave birth to their suns. Thus, the chemical composition of the star should tell us something about the planets which form around it. Before there were any stars, the only elements in existence were hydrogen, helium, and lithium, which were produced in the Big Bang. So the clouds that formed these first generation stars contained only these elements. Friction caused the clouds to flatten into disks, and an aggregation of gas in the center became a star. Planets form at various distances from the star out of whatever material happens to be solid at that distance. Hence, some scientists expected that planets would be less common around first-generation stars and more common around subsequent generation stars. Our own sun is believed to be a third-generation star. In the star itself, there will be a balance between the forces of gravity, which will pull the matter of the star towards the center, and nuclear power, which will heat the star up, causing it to expand. All the naturally occurring elements heavier than hydrogen, helium, and lithium, up to and including iron, are produced by this slow process of fusion. Elements heavier than iron must be produced in a more violent, chaotic process of fusion, which occurs when stars undergo their explosive deaths. The heaviest stars leave behind a black hole. Somewhat later ones that are nevertheless much heavier than our own sun leave behind neutron stars. This theory led scientists to believe that when we discovered worlds around other stars, their solar systems would be much like our own, with terrestrial planets closer to the sun and gas giants further out. Terrestrial planets are planets like the Earth. What has surprised scientists is that many of the worlds we discovered can be described as hot Jupiters. These are planets which, as the name implies, are gas giants, but are much closer to the sun than is the case with gas giants in our own solar system. This caused scientists to revise their thinking on the evolution of solar systems. The current thinking is that the initial planets formed by the process described above, just as the scientists initially thought, but that in some cases there was some gas and dust left over from the formation of the planets, and that this slows the gas giants down so that they spiral in towards the sun. And this also caused scientists to revise their thinking about what planets would be out there, since the same process would eject some planets from the solar systems altogether. As the gas giant went in, it would like kick off some smaller planets, so that they'd be just traveling through space without any star. Scientists suspect that the reason why hot Jupiters are so common among the extrasolar planets that have been discovered is owing to the method by which they were detected. The most successful method at this point has been the transit method, and that is when the planet passes in front of its star, the amount of light detected from the star decreases for a period of time. And in order for them to be confident that it's a planet and not something else causing the dip, they have to observe it dipping at a regular interval. And that means that because they haven't been looking for a long period of time, that they're going to detect planets that are closer to the sun and have a smaller orbit. The other most common method has been to observe changes in radial velocity. When they can determine how fast the star is getting closer or further away from us. And that's caused by, the wobble is caused by the planet and the star orbiting their common center of mass. Okay, so both these methods favor the detection of hot Jupiters, yet with the radial velocity, the heavier the planet, the larger the effect is going to be. And if it's closer in, you're also going to, it's also going to be easier. And in spite of this, the closest known exoplanet is an Earth-sized one orbiting the star closest to our own, Proxima Centauri. And Proxima Centauri is a red dwarf. It's smaller than our sun, and the planet orbits closer to the star. Based on a large survey of stars in a certain area of the sky conducted by the Kepler Space Telescope, Scientists believe that up to a fifth of the stars have Earth-sized planets in their so-called habitable zones, the distance from the star where water can exist in liquid form. In addition to the distance of the sun and mass of the planet, we should also be interested in the eccentricity of its orbit. Any planet orbiting a star will have an orbit that is close to being elliptical. There are like minor variations, perturbations caused by the influence of other planets, but they're mostly elliptical. But some are closer to being circular than others in their orbits. And our own solar system, the planets have much more circular orbits than the ones that they observed earlier, leading some scientists to believe that our own solar system was an exception, and that most ones would have planets that are much more elliptical. And the reason why this is important is because if a planet is circular, it will be a more or less constant distance from its star, and that will avoid large variations in temperature that you would expect if it has a more elliptical path and is constantly getting further away and closer to its star. And also, the reason for this detection may also owe to the methods of detection that they used. You can't really get a lot of information about a planet's eccentricity by the transit method because as the planet's going in front of the star, it doesn't really change its distance that much during that short period of time. But the radial method of measuring the differences in the radial velocity by the Doppler shift to determine how fast it's going toward or away from us is how they would determine how eccentric its orbit is. And a planet that was a more elongated elliptical orbit would get closer to the star and have both its velocity and the velocity of the star would be greater, have a greater maximum, and that would make it easier to detect. I should note that the first extrasolar planet to be discovered was even more of a surprise than hot Jupiter's. It was discovered orbiting a pulsar or neutron star. Scientists believe that the explosion that marks the transition between the normal life of a star and the neutron star that it leaves behind would be so violent that it would knock any planets out of its orbit. For this reason, scientists were very surprised to find planets orbiting a pulsar. And again, this is probably atypical. The reason why you detect it was one of the first is that if it's orbiting a pulsar, that gives you an easy method of detecting it because you can detect like small differences in the timing of the radio pulses that it gives off, that the star gives off. In addition to Earth-like planets, there has been some interest in planets with subsurface oceans. A look at planets in our own solar system has shown that this is more common than we initially thought. Most scientists believe that liquid water is necessary for life, and that life is likely to be carbon-based. There has been some speculation about silicon-based life, since silicon is an element that is in the same column as carbon in the periodic table, so it has some similar properties. But carbon is much more flexible in the number of chemical compounds that it can form. Another way of looking at the same problem is to think about where silicon-based life would be if it were likely to be found anywhere. And that because of the way that scientists believe that planets form, you'd expect more of it like here on Earth, actually, because the cosmic abundance of carbon is there's more carbon in the universe than silicon, but here on Earth, because of compounds with silicon and oxygen are solid. We're solid at the place where the Earth formed, so that's why the Earth silicon is much more common than carbon. It's like the reverse of the cosmic abundance. And so if you would find it anywhere, you'd find it here. You don't find it here, so that gives us good evidence that it probably is rare or non-existent elsewhere. Life needs some sort of energy source. Some examples are energy from their suns, energy from tidal interaction, and energy from radioactive decay. Scientists have discovered that tidal interaction between Jupiter and Saturn and their moons has been sufficient to sustain subsurface oceans of liquid water, even though they were expecting that those places were so far from their sun that any water would be frozen. And that's caused some scientists to speculate, well, if you had like a so-called rogue planet that's been ejected from its solar system, is just wandering around freely without any star, that it might have conditions that are suitable for life, because you could have a gas giant and orbiting satellite with the subsurface ocean, both ejected together, wandering through space. I will close with some thoughts on the Fermi paradox. Given that planets are so abundant, this leads straight to the question, where is everybody? Recent things I've read led me to push me to support more in the direction of supporting the rare Earth hypothesis, which is that common life is rare in the universe, which I was initially not giving a lot of weight to that, and that's because they pointed out that a spacefaring civilization would be able to colonize the galaxy, for example, in about 30 million years. This is sounds like a long time scale, but it's very short compared to the 4 billion year history of Earth. And if you had a lot of life out there and complex life, then it would 30 million years would be probably small compared to like differences in how advanced the various civilizations out there were, or whether life had developed a civilization. And like we can view the time scale of humans that's have been around from 5 to 7 million years ago, and hundreds of millions of years for complex life that didn't have a human intelligence. And then billions of years before that, where there wasn't any complex life. In a recent talk I saw at the Museum of Flight, Robert Zubrin, who's the founder of the Mars Society, was out promoting his book, The Case for Mars, and that advocates exploration, definitely, and later colonization of Mars. He expressed the viewpoint that there was some evidence for a colonization event on Earth, because there's nothing, there don't appear to be life forms that are simpler than bacteria. Like you should be able to see life forms that are, there's this gap in complexity of living organisms. There's between like what we would think would be like the simplest life forms that are barely more complex than inanimate matter, and bacteria. And he pointed out that it could be that the more complex life wiped out the earlier, more simpler organisms, but that doesn't seem to be the pattern now. Well, like bacteria are still around, and there really isn't. They seem to be doing quite well. Yeah, some people have expressed some concern about contact with extraterrestrial civilizations and thought that this would be dangerous and cataclysmic for our own civilization. I personally haven't been quite as concerned as others, although caution is always warranted. It's better to be safe than sorry. But my reasoning is, like, why would an extraterrestrial civilization just wait around all this time until there's a civilization here with things like atomic weapons that could make an attempt to like wipe us out? Somewhat unpleasant for them. But of course, as I said before, better safe than sorry. We should be careful. The hopes and fears of potential contact between us and an extraterrestrial civilization drive much interest in exploring our universe. Alternately, if we are alone in the universe, or more likely the galaxy, then perhaps we can look forward to colonizing the galaxy in the next 30 million years or so. In either case, we will want to know what is out there.